Hey, howdy, space nerds. Are you liking this podcast so far? Well, Are We There Yet is supported by listeners just like you. So consider showing your support with a financial contribution to WMFE. You can do that by visiting WMFE.org/support. Your gift helps us better explore exploration. And thanks. From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast that asks the question, are we there yet? Hi, I'm Brendan Byrne. NASA and its academic partners are about to do something they've never done before. They're going to launch a spacecraft, meet up with an asteroid, collect a sample of regolith, or dust, from the surface, and return that sample to Earth. OSIRIS-REx is set to launch from Florida Space Coast September 8th on a 7-year mission. Now, before it got loaded onto the United Launch Alliance Atlas V rocket, I had the chance to visit OSIRIS at the Kennedy Space Center. There, after an intense clean room dress and decontamination, I met Dante Loretta. He's the principal investigator of the mission, and he was kind enough to give me a tour of OSIRIS-REx, and we'll hear a little bit later in the podcast. But first, just what are they hoping to find? And better yet, how in the world are they going to pull this one off? Well, to give us the details of this historic mission, I'm joined by Robin C. Mangle. He's a reporter at the New York Observer, where he covers space. He's also a contributor to Popular Science. Robin, thanks for joining me.
Thanks for having me, Brendan.
So let's start with the spacecraft. It's called OSIRIS-REx, which stands for Origins Spectral Interpretation, Resource Identification, Security, Regolith Explorer. That's quite a bit of mouthful, but break it down for us. What is this thing actually going to do?
Well, the bottom line is it's a probe, and it's built by Lockheed Martin. They have experience building probes. They built the Juno spacecraft. While it is a probe, it has a mission unlike any other probe has ever had in NASA's history. It has to travel 1.2 billion miles, grab some rocks off an asteroid, and somehow make it back to Earth with this package. The probe is not actually going to touch down on the asteroid. The scientists are calling it a KISS, which is pretty cool. But it has an extension arm on it, which will help grab the material that it needs. The function is to do more than one investigation. And the two primary ones are the sample return and to map the surface of the asteroid for the purpose of knowing where this asteroid is going to be in the future. It's kind of terrifying how close it's going to be to Earth. So that is the one of the security type purposes of the probe.
It's kind of an insane mission when you think about it. It's this little probe. Yes. It's about this. Would you say the size of a U-Haul van, maybe?
Maybe smaller. Yeah. It was actually shockingly small when we visited the other day. But yeah, I'm kind of always surprised by the size of probes when you see NASA's cool CGI videos and you see them launch on these like humongous skyscraper type rockets, but they're actually really small. It's smaller than a Volkswagen Beetle or something, but they're doing incredible things and they're traveling extremely far.
Yeah. So this thing, it's launching in September.
Yes.
Heading it's going to park itself in an orbit around the sun and then head to asteroid Bennu. Can you kind of tell me about the mission itself?
Yeah, let's go through the actual mission, which is coming up on September 8th. After the Atlas V lifts off with the probe, it will obviously detach, and the probe will actually reach a escape velocity of around 12,000 miles per hour, and it'll start its journey. It's a long one, a 2-year journey, and it'll travel its 1.2 billion miles, and when it arrives, there'll be a complex maneuver, and it'll have to intercept that asteroid.
How big is this asteroid it's coming up to?
It's 1,600 feet in diameter, which about a mile. Yeah, and it's a relatively small celestial body, but the implications of this asteroid are incredible. We're calling it a time capsule because the asteroid has preserved material that could be as old as over 4 billion years old. Now, that is when the solar system was actually formed. And the asteroid kind of acts as a preserve for minerals and, potential organic life.
Prebiotic, I think they called it. Right?
Yeah, exactly. And that's what NASA's hoping to find there. They know it's a carbon-rich asteroid, and they really want to find organic material there. Or, as the scientists on the project would say, the building blocks of life. They're not looking for life, the building blocks. And it's important to note that. And what that can tell us is what was happening 4 billion years ago when the solar systems were being formed? What was happening on Mars? What was happening on the moon? What was happening here on Earth? That's the most important question.
It's kind of like a solar system fossil.
Exactly.
Right?
Yes.
Kind of unboxing what actually happened before we were around.
Yeah, it's like a tape recorder. It was just this asteroid was just watching this whole thing happen, and it just captured everything like a vinyl record.
Now that there's two very distinct portions of the mission. There's that science portion we talked about, looking for those prebiotics and grabbing that sample, but there's also kind of the security portion of it. They want to find out how these things behave in orbit. Can you kind of walk me through what they're hoping to find there?
Yes. Okay. Well, there are two principles that dictate how a small celestial body like Bennu moves. And one are photons that are emitted from the sun. They kind of create pressure and, throws it off its orbit a little bit and could change its trajectory. But the Sikorsky effect is what they're studying. Now, in simplest terms, one side of the asteroid, really hot, one side really cold. Obviously, the side facing the sun. And this is actually what kind of governs the position of the asteroid and where it's going. And, we do know some stuff about the Sikorsky effect, but NASA needs to know more. And I want to cite Jim Green here, NASA's famed, planetary scientist. He always says that we need to get to Mars. We need to colonize Mars because at some point in the future, one of these rocks out there is going to intercept with Earth, and it's going to hit us. Now, in terms of Bennu, you'll read some headlines that'll say, "Oh, it's deadly. It's dangerous." The chances of it hitting us right now are very slim.
Well, that's good to know.
Yeah. Even if it does, we're not gonna be alive, Brendan. So in the year 2135, they're saying it's going to come within 186,000 miles of Earth. Now that's closer than the moon. A little, that stresses me out a little bit, but a lot of things could happen by then. Like I said, the sun's photons could alter its trajectory a little bit, or this Sikorsky effect, what side of the asteroid is going to be facing the sun. And now for them to study this, that's the big chunk in this mission, over 500 plus days. Now, what's going to happen is when they reach the asteroid, it is going to survey the entire rock. And they're just going to map it and survey it. And that will allow them to, grid by grid, see where this heat is, where is it coming off, where it's going in. And, they'll have an actual model to, Bennu might end up being the standard for how we measure the Sikorsky effect someday. So,
right, it's not just to measure where Bennu is going to be in that year 21 or whatever it is. It's to use it for other celestial bodies.
Exactly. Like they're going to make it a standard. It'll be the first time to actually fully map something like this. And they're going to be able to measure where it's going and how far it's going.
So no need to call Bruce Willis just yet, right?
Not yet.
We should be okay.
Yeah. So
this mission, it's launching September 8th, as you said. It's going to take quite a bit of time there. About how long is this mission duration?
Oh, well, it's going to take 2 years to get there. And once it's there, 505 days, I believe, is the exact amount it'll spend there. And on it's going to have to take another journey home, a round trip. It'll be back in 2023. Which I hope you and I still have jobs so we can cover that. Maybe we'll be back here.
Yeah.
But yeah, it'll be back in 2023, hopefully with 60 grams worth of scientific material that will benefit generations to come. And I want to recall the Apollo missions because that was the last time we brought back that, a significant amount of material. We're still studying that material today.
Being NASA in the U.S., right?
Yes. And, so, one of the things that these scientists and researchers are stressing, they're saying that this material and what they bring back will be studied for generations to come by scientists who haven't been born yet. And they're going to be answering questions we're not smart enough to ask yet.
That was the most coolest thing I caught from that is 75% of this material that they're getting is going to be archived and slowly released over the years and to other organizations, not just NASA. They're sending it, worldwide.
Oh yeah, I mean this research is not just for Americans. This is, this is a human a mission. And obviously NASA's pioneering it, and those are incredible researchers. But this science will be available for generations to come. And obviously we both know that, scientific study, that's a benign diplomatic platform. We share information with the Russians, the Chinese, the Indians, and that will not change for this mission. There will be, I've been told by these researchers that the instruments that they're going to be using are going to be as small as a computer or as large as a building to measure this stuff and really analyze it. It'll take years. It'll take people who are not born yet, like I said.
Yeah, it's fascinating stuff. Now, both of us got the chance to check out OSIRIS-REx in the Payload Hazardous Servicing Facility at Kennedy Space Center. Now, we'll talk a little bit about what that meant for reporters, but while I was there, I spoke with, as you mentioned before, Dante Loretta. He's the principal investigator of the mission, and he gave me a tour of the spacecraft. Let's take a quick listen to that.
OSIRIS-REx, the star of the show is the TAG-SAM device, that touch-and-go sample acquisition mechanism. You can see the shoulder joint that's attached to the science deck over there on the right.
That's what's in black there?
Just to the right of that. And so that's the upper arm segment. That's that pole that you see going down to the elbow down there. And then the forearm, this part of the arm is where that black mylar is wrapping around. And that black mylar is covering the gas bottles that we will open up for the sample collection event. We have 3 of those on there. The plan is 1 successful sampling attempt. So the hope is we plan it, we do it once, we get the sample, and we're done. But we have contingency, and we have backup and redundancy, and so there's 2 other opportunities to perform that. The sample head is contained in that launch cover, which is like an octagon-shaped panel that you see there. That's there to keep the sample head clean during the big burns on our main engines, which are hanging off the bottom of the spacecraft down there.
Oh, those little guys there.
Yeah, they've got the red caps on them and the removable before flight tags attached to them. Those are the 200 Newton thrusters that we'll use for our big maneuvers in interplanetary space.
They're pretty little for all that power, huh?
That's right. In between, you can kind of see 2 little thrusters that are our ultra-low thrust rocket engines assemblies. Those are 0.2 Newton thrust, so 4 orders of magnitude less, and that's for precision maneuvering around the asteroid. You can see 1 trajectory correction maneuver thruster that's hanging out down at the bottom there. That's around 22 newtons of thrust, and that's there to keep the spacecraft vector aligned during those major burns on the main engine so that we keep the direction of the thrust where we need it. And then finally, on each corner of the spacecraft, there are 2 attitude control thrusters for full redundancy. And they're there to keep the spacecraft pointed in the direction that we want to. And more often, we'll be using our reaction wheels, which you can't see because they're in the interior of the spacecraft. Basically, mechanical flywheels. You spin this way, the spacecraft spins in the opposite way. So we use those for precision pointing. But the momentum will build up on those wheels, and you have to get rid of that momentum, and we do that by burning on the attitude control thrusters and using the chemical energy to compensate for the mechanical energy in the flywheel.
Because a portion of the mission is kind of hanging out above the asteroid,
we will spend at least a year and maybe a little longer mapping the asteroid in great detail. We are a fantastic remote sensing mission, and the best that will ever have flown to an asteroid in history. So we'll get a phenomenal amount of information about asteroid geology and dynamics and rotation and all of that. You can see some of the science instruments here with the white panels that it's just to the left of the TAG-SAM. That's the OVIRS, visible and infrared spectrometer. And then the kind of ice cream scoop looking device right behind it is the thermal emission spectrometer, or OTES. And then the big guy behind it is the Polycam. That's a reflecting 8-inch telescope. And it's called the Polycam because we'll use it to find Bennu when we're 500,000 kilometers away. But we have a focus mechanism, and when we're 200 meters from the surface, we'll get microscopic-like shots of the asteroid regolith. If we scoot over a little bit here, you can see another smaller imager to the side. That's the
little gold cap there?
Yeah, that's the map cam. So that's kind of our workhorse. It's a refractive system, optic system. It's got a filter wheel that's got a panchromatic filter, but also 4 color filters, so we'll get color imagery of the entire asteroid surface.
Kind of flips around.
It just kind of moves through the different filters, and then we'll downlink each image on the ground and combine them into different color images with image processing software. You see the red handle. That's right. That's covering the OLA. That's the OSIRIS-REx laser altimeter, which was provided by the Canadian Space Agency. It's got 2 energy lasers, one for when we're far away from the asteroid and one when we're close to the asteroid, and a 2-axis scanning mirror. So it will raster the laser beam back and forth across the asteroid surface and very rapidly build up topographic maps of the areas that we're investigating. So you can also see kind of two optical paths that are pointing off in that direction below the science deck. Those are our star trackers. We use those as part of the guidance system. So the spacecraft has a star catalog in its memory. It uses those star trackers to make sure it's in the right orientation.
That's interesting. That's cool.
And then the device that's kind of pointing up above that is a low-gain antenna. So that's got basically a hemispherical radiation field. So it can talk to the Earth if it's anywhere in there, but at a very low data rate of about 40 bits per second. If you want to walk around, we can look at the back of the spacecraft and see some of the other antennas. These are the solar arrays right here. We have two of those, about 4 square meters each, and that provides us around 1,200 watts of power, which for a spacecraft is actually quite generous. The solar arrays are on 2-axis gimbals, which are kind of you see the white harnessing that's coming down there, almost looks like a little heart. So the solar arrays can fold out towards us so that they're parallel with the high-gain antenna, which is this 2-meter dish that we see pointing off in that direction there. They can also rotate this direction. You've probably seen the classic Y-wing configuration when we're sampling, and the strategy is just get them as far away from the asteroid surface as possible. Hanging on is a second low-gain antenna that's pointing down there, and then a medium-gain antenna, which is the device that's right above it there. And if we swing around here, you see the kind of rectangular box. It's behind a sunshade, so it's a little tough to see. That's the Rexus regolith X-ray imaging spectrometer. That's a student experiment that was built by undergraduates and graduate students at MIT and Harvard. We actually had an open call for student collaboration experiments on the mission.
You've obviously spent a lot of time, a lot of energy, a lot of work on this spacecraft. What's it like seeing it in the high bay here and knowing that in just a few short weeks it's gone?
It's been an incredible journey to get to this point in time, and I'll admit to having a lot of nostalgia and just emotional moments watching this vehicle and getting ready to see it encapsulated in this payload fairing. I wish OSIRIS-REx well on the journey to Bennu back, but I will admit to missing the opportunity to come into this clean room and see this amazing piece of engineering and the team that has worked so hard to make this a reality.
That was Dante Loretta, principal investigator of the OSIRIS-REx mission. Now, in the studio here with me is Robert Seamangle. He's a reporter with the New York Observer and contributor to Popular Science. Robin, you were also there in the servicing facility. It was a pretty strict contamination protocol, something we've never run into before.
Yes,
Can you kind of tell me about it?
Well, I feel like you and I talked the night before. We were up late stressing. Mm-hmm. We got multiple emails over a course of a few weeks, and they might as well have put no nylon in the subject line because that's what the emails were about. No nylon, because, one of the materials that they're looking for is amino acids, which is a building block of life. And materials like raw leather, hair, nylon, these, they could contain amino acids. So, I don't know about you, Brendan, but I was checking the tags on everything I own, my socks, my shirt, my underwear. We all showed up that day at Kennedy Space Center sweating and panicking, and NASA was just overly cautious, which it's well within their right. I mean, this research and this mission is so important, and we've only got one shot at it right now. We all know how expensive these missions are. So, yeah, we were all going out of our way. But, yeah, the main thing was no nylon. They really were crazy about that.
Now, it was also full clean room protocol. Like a lot of times when they let reporters see these spacecraft, you have to put the blue bunny suit on. You go through the air shower. I have to cover my beard up. It's a process. But just to add one more level with that nylon, and why specifically the nylon?
When nylon interacts with organic material like your skin or hair, it produces amino acids,
and that's what they're looking for.
Yeah, and if we're in the clean room and you and I are in the clean room and the spacecraft already detects it, that screws up the whole mission.
Yeah.
So that was one of the main things. When it comes to hair, I have no idea, Brendan, how they covered that thing up on your face.
It was hard.
Yeah, a lot of the other reporters shaved.
I thought about it.
No, but yeah, it's. And like you said, we've been in the clean room before to visit the Cygnus spacecraft. Those were such a casual. Those were much casual than this time around. I really love seeing the fairing where the fairing is on top of the rocket. They actually had it open in the facility in the high bay, and you could see inside of it. And NASA and Lockheed and all these other companies, they always design these great logos and patches and stuff. And it just looks like a great. The rocket design is really great. The logo is really great. And just a few feet away was OSIRIS-REx, just sitting there, looking beautiful, ready to be loaded into the rocket fairing.
Mm-hmm. And for our listeners who might not be familiar, that's the part on the top of the rocket that encapsulates the spacecraft, and then it's kind of blown apart once it gets to a particular altitude.
Exactly, and that's when it starts its like push, away from Earth. But yeah, you're right. It's and I'm guessing at this moment, or today or tomorrow, they're going to move OSIRIS-REx into that rocket fairing, close it up, and if you haven't seen it, it's just like two sides. And, they close up and circle the probe.
We heard a bit about how it's going to collect this sample, and it's using this arm. Can you kind of walk me through this really neat tool that's on OSIRIS?
In the best way I can, it's okay. OSIRIS-REx will not land on the asteroid. It's we have to be clear about that. It's going to hover right above it. The only part of the spacecraft is this arm that you're talking about. Now, this arm's going to extend, and that part is actually going to touch the asteroid. The arm is going to push out a burst of nitrogen
to blow on the surface.
Yeah, exactly. It'll blow on the surface, and it'll agitate the surface, and small, tiny particles are going to float into the air, and it'll get scooped up by the air filter. Now, this has to happen in a matter of 5 seconds, which is incredible because this is one of the major objectives of this mission, and that's the time duration.
The 7-year-long mission.
Yes, 5 seconds it comes down to. But on the other hand, they have 3 chances at it. So in case there is in that 5 seconds, it'll grab that material, it'll float away, but it's going to stay within distance to try again if they need to. And they have 3 bursts of nitrogen to use. I would have packed one more, but this is what they've got, right?
Hey, weight is crucial on a spacecraft.
Exactly. So they're hoping to gather 60 grams or 2 ounces of this regolith material, and hopefully this material has what they're looking for, what we're looking for, and something that can teach us about how this whole thing came about. The 8 planets or 9, depending, but. So it comes down to 5 seconds, which is incredible, and then it'll start its journey back to Earth after that.
Just to kind of recap, we're looking to bring back this sample. Hopefully, it has prebiotic organism and compounds on it that can be the keys to the early chapters of how life formed on our planet and in the solar system in general.
Right.
We're also looking to map Bennu. We're also trying to figure out what kind of effect heat and the sun's radiation have on the orbit of this asteroid and other asteroids within our solar system if they're a threat to us. Robin, as a space journalist yourself, what is the most exciting thing about this mission to you?
Well, it's the same thing for every mission, learning about who we are, where we're from, where did this planet come from, how did organic life reach this planet? These are the fundamental questions about life. And this is why so much work goes into these missions. I mean, you're going to read, we're going to collect some rocks. Yes, but the implications for that are incredible. And this is never going to stop. This research is not going to stop. When we bring that bag of material back, we're going to be studying it for years. Our next generation, the generation after that. And we're going to learn things that we've never even thought to ask about before, which is incredible.
I've been speaking with Robin Seabangle. He's a reporter with the New York Observer and a contributor to Popular Science. Robin, thanks so much for stopping by.
Thanks for having me, Brendan.
Well, that's going to have to do it for this episode. Support for Are We There Yet comes from the listeners of WMFE. You can follow the show online. We're on Twitter at AWTYMars. Are We There Yet Mars? Get it? Or reach out to me in the Twitterverse. I love to hear from listeners. I'm at Space Brendan. Leave us a review on iTunes. That's how more people learn about this podcast. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. For more space news, visit us online at WMFE.org/space. Until next time, I'm Brendan Byrne. Thanks for listening.